Okay, so today I have an interesting topic, Penrose diagrams. Some of you have probably seen Penrose diagrams, and the one you're familiar with is probably the Schwarzschild metric Penrose diagram, which I will be drawing. My goal for this lecture is to be an overview of what Penrose diagrams are and how to derive one. So I'll do that with a Minkowski in space because the algebra is nicer and doable in one lecture period. But before we do that, I want to start with something we did in class. So on September 1st, Kruskal, of 1960, Kruskal publishes Maximal extension of the Schwarzschild metric. And in this paper, he does what we did in class. He lays out the Schwarzschild metric, goes through the coordinate transformations, and I will just go ahead and write down the metric that we derived in class, ds squared. I think we had a 4rs cubed over an r. And then this was our decaying exponential, which is the conformal treatment. And then this was multiplied onto something that resembles Minkowski in space-time, where dt is a time-like coordinate and dx was a space-like coordinate. This is the equatorial approximation. There's a minus r squared d omega squared. Not going to worry about that. But the beauty of this is we have something that resembles flat space-time with a conformal treatment, where r in the denominator and exponent are implicit functions of t and x. So the reason we love this so much is because we can go and still draw our light cones, our null geodesics, and see what happens at infinity as if it's a point. So I'll just remind you guys what we got when we did that in class. And this was our, wow, these lines are not straight. No, it's not. Yeah, all the professors make it look so easy when you guys have been doing this for so long. So here we can see that our r lines were hyperbolic, looking like this, and that our t lines would run straight out like this. So these are our t lines, and these are our r lines. And then this conveniently allowed Kruskal to separate this new space into 4 separate regions that he named, well, region 1, 2, 3, and 4. And all of this is a review. This is what we derived in class. But this will be very important when we move to the Schwarzschild Penrose diagram. And then I'll be going off of Sean Carroll's 1997 notes. He did a course at MIT and made his notes publicly available before he wrote his textbook. I think it was 99 that he published, his GR textbook. So I will just simply start with the Minkowski metric. Something we all know and love, dr squared. Again, I'm going to make the equatorial approximation because it's just easier. We all know that. We love that. And the first coordinate change he did, well, I guess I should mention, this follows a similar process that we followed in the Kruskal extension, where we went through a bunch of coordinate transformations and ended up with something that preserved a time-like and space-like coordinate. This is a similar process, but we're not actually doing a full analytical extension. We won't do that until we get to the Schwarzschild metric. So the first transformation he did was the null coordinate change. And I would like to stress this is different from the null geodesic. The null coordinate change are just the coordinates that lie along the light cones. So we end up with something that looks like this, which allows us to explicitly solve for t and r in terms of u and v. And I'm pretty sure we did something extremely similar in the homework. I think this might have been on our first homework. So, I mean, we all know how this goes. dt squared, differentiate, and this is just a difference, or this term squared. So du squared plus twice the cross product, or I'm sorry, the cross term, dv squared. And then dr gives us a very similar thing, where it's minus the cross term, and then plus dv squared. And something interesting happens when we actually go ahead and calculate ds squared is the g naught naught and g11 terms go away completely. And we have a metric that is entirely the cross terms. And it would be 4 times the cross term. I'm going to separate it out. So we have 2 times du dv plus dv du. Yes, that's 4 du dv, but I'm doing this so I can label g naught 1 and g1 naught. So that's interesting that we have a metric that is entirely cross terms. There's no g naught naught or g11. So this was a simple coordinate transformation. Now we're in the null coordinates. These would follow the light cones of Minkowski in space. So what we're going to want to do is we need a conformal treatment for us to take all of Minkowski in space and shrink it down into an infinity, or take an infinity and shrink it down to something I can just draw on a napkin if I wanted to. So the treatment we'll use is we'll take u prime and denote it as arctangent of u, and same thing for v. And I'll remind you guys what the arctan function looks like. Just does this. And it takes on a maximum value at pi over 2 and a minimum value at negative pi over 2. So I can put in positive infinity in x, negative infinity in x, and I'll never get a value that goes beyond pi over 2 or negative pi over 2. So this will take care of our conformal treatment. Again, we can just explicitly figure out what, I'm sorry, this should not be primed. Yeah, we can explicitly figure out what u and v are, and we should just get u equals tangent u prime and v equals tangent v prime. So we're looking to construct this metric using this transformation. So it's pretty simple to find what du equals a secant squared of u prime, and this would be du prime, and dv is going to equal secant squared of v prime, dv prime. So we can just plug these in, and I'll just show you what ds squared ends up being. And I want to do that. I'll do that down here. That'll be fine. And this is not any different than any of the coordinate transformations we've been doing in all of our homeworks. So we just end up with something that looks like 2 secant squared u prime, secant squared of v prime, and that's factored out of this du prime, dv prime, plus dv prime, du prime. That's a v. Again, there's still no g naught naught or g11 term. This is still a metric that is comprised entirely of the cross terms. So I'll just go ahead and label this as g naught 1 and g 1 naught. And then that secant squared term just factored out of the front of these. So this is our conformal treatment. And we can already see the parallels to the Kruskal metric, because although I don't have something that looks like Minkowski in spacetime, I've lost metrical meaning because I went ahead and squished it with this arctangent function. I have some amount of metric terms here with a conformal treatment out front. And this is telling us this is a conformal treatment of the null coordinates of our original T and R. So now our goal is to, okay, we need to restore the space-like and time-like nature so that we can get a metric where I can actually construct light cones. So that is what we'll go ahead and do now. And this is where the math gets, I'm going to explicitly go through all of the algebra. It's a bit long-winded, but I want to show the full process to get to a Minkowski and Penrose diagram, because there's just not time in one lecture to do that for Schwarzschild. But I want to show that process so that I can then just go ahead and write down the Schwarzschild Penrose diagram, and we can go ahead and discuss it. So goal, the restore time space-like coordinates to that metric that has our conformal treatment. And we'll do this by putting u prime and v prime to eta and chi, where eta is the time-like coordinate and chi is space-like. And this is a pretty, well, before I show you what the transformation is, we'll show the transformation, because this is eta equals u prime plus v prime and chi equals u prime minus v prime, a simple transformation. But I'm going to impose restrictions on the bounds for eta and chi. Eta will take its full range, which will be an element of negative pi to pi. And we get that because it's just a sum of our u and v, which themselves range from negative pi on 2 to pi on 2. So that just gives you negative pi to pi. But for chi, I'm going to intentionally restrict it. Sorry, chi. And this will give us 0 to pi. I'm not going to let it range over the full range. And we'll see why I'm going to do that once we get to the Penrose diagram. So this, again, allows us to explicitly solve for u prime and v prime, and we get eta plus chi over 2, and v prime being eta minus chi over 2. Okay, so now the goal is to take that thing and express it in terms of eta and chi. And it's not very fun, but I'm going to go through and do the full thing. So I'll go ahead and rewrite the ds squared as 2 over cosines. So this would be a cosine squared of u prime and a cosine squared of v prime, and then multiplied onto the metric terms. Let's say du prime dv prime plus dv prime du prime. Okay, so now I'm going to work with this conformal term out front first, and then go and work with the metric terms. The metric terms are much easier, so I want to deal with this first. And I will just let omega equal the non-squared version of that. So just cosine u prime, cosine v prime. So that if I wanted to write this out, this would be 2 omega to the negative second power. And the reason I want to do this is because I can take this and say, well, this is just cosine of eta plus chi over 2 times cosine of eta minus chi over 2. And we have summation identities for these. So we know that I can write a sum of 2 angles as cosine cosine minus sine sine. So I'll go ahead and, it's minus, right? Yes, it is. Okay. So we'll get this equaling cosine of eta over 2 cosine of chi over 2 minus sine eta over 2, that's not an eta, and then sine of chi over 2. And all of that is multiplied onto a cosine of eta over 2 cosine chi over 2. And then minus sign gives us a plus sine eta over 2 sine chi over 2. This looks awful, but it's just a difference of squares. So first term squared minus the second term squared. And that would give us a cosine squared eta over 2 cosine squared chi over 2 minus the sine squared terms. No cross term and a difference of squares. Sine chi over 2. And then we have more identities. These are just the power identities. We know we can express cosine squared as 1 minus cosine of twice the angle over 2. But the good news here is twice the angle just leaves eta and chi in the argument. So I'll write that out, and we will get, this is still omega. And that, with the power identities, will give us 1 plus, it was plus cosine eta over 2, 1 plus cosine chi over 2, and then we have a minus 1 minus cosine, minus because we're dealing with sine now, over 2, and 1 minus cosine chi over 2. This, I won't bore you guys simplifying because we can just distribute it and collect terms, and I'll just go ahead and write out what we get for omega. We end up with 1/2 cosine chi plus cosine eta, or, however you want to express that in terms of order. So now we can go and tackle this, these cross terms, the g naught 1 and g 1 naught, and that's a bit easier to do. So I'll do that up here. Okay, so I do have my metric out there, which is good. So for our cross term, the du prime dv prime plus dv prime du prime, and this is pretty simple. We've already gone and shown what, I guess I didn't go and show what du and dv prime are, but it's just d eta over 2 plus d chi over 2, and you can collect those. And then we have those multiplied on to each other. So there'll be a 1/4 on each of these terms, and then a d eta and d chi squared, because it's a difference of squared with the minus sign here. So that's just simple algebra. And we'll end up here with the 1/4 coming out front, and then a d eta squared minus d chi squared. And then for the second term, it's plus d eta squared minus d chi squared. And this can be simplified down to 1/2. Notice these aren't canceling. We just get a d eta squared minus d chi squared. So I'd like to note something interesting just happened here. We did our last coordinate transformation to the time-like and space-like coordinate, and we got rid of our cross terms and ended up back with something that's g naught naught and g 1 where eta and chi are space-like and time-like. So from a Minkowski point of view, this looks like flat spacetime. it's a time-like coordinate. It's a difference of the square of a time-like coordinate and a space-like coordinate. So that's great. That's exactly where we want to be if we go up and look at our Kruskal metric that we started with. So we now have this part of the metric and this part of the metric. So this is in the denominator and squared. And then there's a 2 up there, but there's a 1/2 here. So I'll go ahead and cancel this 1/2 and that 2. And now we can just write ds squared as 2 over omega squared, and then d eta squared minus d chi squared. So this is where I spent 20 or 30 minutes in my notes wondering why Sean Carroll didn't have a 2 in his metric and I did. And I couldn't figure it out. I went through it multiple times, and well, maybe that should be a 4 because it was squared. Either way, whether it's a 2 or a 4, I spent about half an hour trying to figure out where this constant came from, and it was just irking me because does that mean the whole spacetime is stretched by a factor of 2 or 4? I couldn't figure it out. And Sean Carroll didn't explicitly go over the derivations. He skipped more steps than I did. Turns out these constants just get absorbed into the definition of the coordinate transformations, and he did not make that explicit. So for the purpose of drawing the diagram, he just went ahead and wrote this like this. And the 2 just was waved away. So this now is in the form that our Kruskal extension was in, or the Kruskal metric was in when we derived it. We have something that resembles Minkowski in spacetime, a difference of squares of a time-like coordinate and a space-like coordinate with some conformal factor out front. And that conformal factor is explicitly defined in terms of our time-like and space-like coordinate. So what's happening with this omega squared term is it's 1 over the cosine of the conformal treatments of the null coordinates of our original t and r. So hopefully we've been able to follow all of the coordinate transformations up to this point, similar to what we did with Kruskal, but not entirely the same. I did apply a restriction. So I'll save us the time of going through and drawing what lines of, or deriving what lines of constant eta and chi should look like, and just draw the Minkowskian Penrose diagram. It will end up looking something like this, where these are the bounds, the conformal bounds of our spacetime region. And if we want to draw lines of constant r, they'll run like this. And lines of constant t will run like this. And this is something you guys might recognize as half of a Penrose diamond. And the reason it's half is because I imposed this coordinate restriction here. And I guess I never mentioned the reason why I wanted to choose this coordinate restriction. And if it's because if I asked you to just draw a Minkowski space diagram like we started doing at the beginning of the semester, you might draw something that looks like this, which ranges x 0 to infinity and t ranging from -infinity to infinity. So for the purpose of drawing a diagram that we're used to, I applied this restriction from 0 to pi instead of allowing the full range. So, I mean, it's pretty clear to see that if I allowed the full range, we would end up with a complete Penrose diamond. Let me fix these lines because they're not very good. So this is a causal diagram of a conformal treatment of Minkowski in spacetime. Well, my limited Minkowski in spacetime. So this represents all of Minkowski space shrunk down into a triangle, or I should say half of Minkowski space. And there's a couple key points. This is chi equals 0, this boundary here. This is typically denoted as I plus, and then down here I minus, and this is I naught. And then these boundaries here aren't physical boundaries because they're not a point or a region we can reach within the spacetime. They bound it. They're not part of our original Minkowski spacetime. These are denoted as scri plus and scri minus. So I naught is infinite space. We can go from 0x all the way to infinite x. And if we stood still along some x coordinate, just like we would in a Minkowski diagram, standing still corresponds to that. We just move upwards in time. So our time coordinate lines will always go from -I and then converge back to +I. So the reason we love this diagram is because we can do the same thing that we can do in the Kruskal extension. I can still draw my light cones here, And locally, they'll hold up just fine. And I can trace the path of a photon through this region any way I'd like. But it should be noted that this is an entirely boring result. This doesn't tell us anything interesting. It's Minkowski spacetime. It's flat, it's empty. So yeah, I mean, I can go ahead and draw a light cone like this and just say, okay, well, I'm going to go to some infinite direction. And it should be noted that, like I mentioned, these boundaries here don't represent physical, like it's not a point, because this is some combination of eta and chi. So this would just be akin to, at some time running in some direction into the future, because this is a completely conformal treatment. But this is a pretty non-interesting result. The good news is that we've gone through and explicitly defined how to arrive at something like this, minus me actually solving for lines of constant eta and chi. So now I can go ahead and write out the metric for Schwarzschild and draw the Schwarzschild Penrose diagram, which is the one that you guys are most likely more familiar with. So we can get rid of this, and I'll leave the Kruskal metric and the Penrose diagram over there. So when I draw the Penrose diagram, I want you to look for the Kruskal extension embedded in it. We'll get something, and I'm going to try to draw this with some guidelines. So we'll end up with a diamond here and a diamond here. Okay. And then we continue this on. We have a flat line, and then same thing out this way with a flat top. And then this goes something like that. And these go away. So this is the Penrose diagram that you guys are probably more familiar with. And we can go ahead and label the same sort of points will pop out at us. I naught is over here. I plus is over here. I minus. So this is where this would be the maximally extended single Penrose diamond that I drew in the dashed lines over there. So all of those same points still apply. If I want to do constant R lines, still is going to look something like this. And coming out, going back. And then our T lines, T lines. We'll arrange something like this. And yeah, that's fine. I can draw two more. So we can see this is a completely conformal treatment. And we'll have a similar thing going on for here and here. But by now you've probably already spotted where that Kruskal-like extension comes from. Running like this, these are the null coordinates, the same null coordinates that we did in our treatment of Minkowski. So the beauty of this diagram is we can separate it into the same regions 1, 2, 3, and 4. And it's a conformal treatment of the Schwarzschild metric now, which means we can still draw our light cones. So the null geodesics of this entire diagram just look like cross-hatchings. And from the Kruskal extension, we also noted that this was R equals RS, and the singularity took on this shallow hyperbola up here at R equals 0. And the typical way these are drawn is it's denoted as just this line up top being R equals 0. But with the full extension, we still have regions 3 and 4 to deal with. And we touched on what regions 3 and 4 were in lecture. But I'd like to trace some paths of photons too. This is also a R equals 0 singularity. And I can also go ahead and label this as I plus and I minus and I naught over here, where these are our typical scry plus boundaries and scry minus boundaries, and the same over here. So something interesting going on. There's 2 I plus points, and 2 I minus points. And we should almost expect that the way we've drawn this diagram, because we've shown that the singularity gets stretched out to a line. we know in the Schwarzschild metric that we're not dealing with a spinning black hole. There's no Kerr metric stuff going on here. The singularity should be a point. So as a result of our coordinate transformation, it's drawn as a line. So it should make sense that this point and this point get separated out, and it's really, we can draw the same I plus and the same I minus down there. So interesting things happen when we consider paths of photons in this diagram. That's actually the whole purpose we draw these, is because I can still preserve my light cones. So say I have some starting point here, the 45-degree light cone still holds up, and I can have some particle that will inevitably cross our event horizon at r equals rs, and then some particle that will just go off to the scribe plus infinity. And then same thing for the negative version of the light cone. We have something that looks like it's coming from region 4, or either coming from the scribe minus infinity. So interesting things happen when we consider what's going on in region 3. We know that because the light cones hold up with our d eta minus d chi, any travel in these regions is entirely forbidden. This would be superluminal traveling speed. But if I draw a light cone out here, we can note that these photons can arrive to the same point inside the black hole's interior. And likewise, if I go ahead and finish out this light cone over here, they can originate from the same point too. So this would be akin to somebody sitting in region 4 and shining a photon in either direction. And either way, they're going to exit the white hole, the region 4, but end up in entirely different universes that are theorized to exist. But again, anyone here has no access to this region. They can only meet in region 2 in the black hole. So that's a really interesting result. We have a parallel universe, and both of them have access to the same black hole, and both of them can get things from the same white hole, but they can't communicate with each other. If you wanted to look more into this, this point here is known as the Einstein-Rosen bridge, and there's a paper on that. I don't know when it came out, but I'm not going to go into it in this lecture. But now that we've done this, I will go ahead and show you guys. You had mentioned at the beginning of the semester that Penrose was the only person that could visualize in 4 dimensions. Allegedly. After doing the research for this presentation, I'm convinced that's true. So I'll just go ahead and show his 1964 paper. A lot of the formalism that he used to derive his Penrose diagram is all tensor calculus stuff, and mathematics that's far above my head, but I figured it'd be worth showing. So this is the Schwarzschild, this is Kruskal's paper from 1960. And this is what we went over in class. It's a short paper. It ends right there. But I figured it'd be worth showing to see that he starts with the Schwarzschild expression and does a similar coordinate transformation, actually the same one that we did in class, and ends up with something that looks very familiar down here. This is the Kruskal diagram that we derived and I showed at the beginning of class. So that was the 1960 paper. And then in 1964, Roger Penrose goes and publishes Conformal Treatment of Infinity. This is a republication. The original publication was lost. I can't find it, but there's a bunch of republications.
What do you mean it was lost?
That's a good question. I can't find the original publication anywhere online. It's only republications. So I can't find, like, in the physics journal, I can't seem to find the original 1964 paper that was in. Sorry?
What citation records to that paper?
Is there one?
Which
Like
journal?
the reference list.
I don't have it, but let's see. Original paper about relativity, roots of topology. So 1964, reprinted. So yeah, relativity, roots of topology.
Was some collection, I guess.
Yeah, and I was unable to locate it there, but there's a bunch of republications of this paper. So I'm not going to, well, there's not time in one lecture to go in detail through all of the tensor and field analysis that takes place in this paper, but I thought it would be worth showing some of the diagrams. This certainly looks like he's able to visualize in 4 dimensions. I really am not sure what's going on here. This is a hypersurface, so a 3-dimensional surface. He's much more brilliant than we are, and it would take a long time to unpack this paper, but I do want to just skip through this a bit and show the first Penrose diagram that we saw appear in a paper, and that's this one here. This is drawn differently than I've gone and drawn the Minkowski one. Here, time is running up, and these capital I's would be akin to our lowercase I naughts. So this is rotated down and just drawn differently, but the boundaries still hold up. And that would be more similar to the restricted half diagram that I started with Minkowski and spacetime. And then he draws another one. These rely on something called de Sitter spacetime, which is far above me and would require many more lectures to go into. But just for fun, I thought I'd also show, these are known as Penrose-Carter diagrams because Brandon Carter was the person who popularized their use in this typical diamond triangle fashion. So he published a paper in 1965, Complete Analytic Extension of Symmetry of Kerr's Solutions of Einstein's Equations. I know we all love the Kerr metric, and it's so much fun to work with. So there it is in all of its glory. And this paper goes through and applies that same methodology that I used to derive the Minkowski diagram and the same methodology that you would get the Schwarzschild diagram from, and does that for the Kerr metric. And it's exactly what you'd expect. It's so much math and algebra. But once you get time to drawing diagrams, you end up with things that look like this, where you end up actually with a tiling of Penrose diamonds, where the extension up here would be a white hole on top. So the paths of photons that you could take would sort of weave through this tiling of Penrose diamonds as you go up. So it could be that you would start in region 1 and go into a black hole, continue through the singularity into the white hole, and out into another region, well, 1, 2, 3, 4, maybe like a region 7 universe. So these things get crazy, and I thought it would be worth showing. This is for a charged rotating black hole denoted by the Kerr metric. So yeah, with that, that will conclude. So are there any questions on any of the things I did? I know that was a heavy derivation, but hopefully this makes more sense now. Yes?
So region 1 is all of space.
Yes.
Like the entire universe.
Yes.
Okay, well, this is assume that there's only one black hole in the universe.
Yeah, this is a pretty simplistic treatment. A non-astrophysical black hole, a theoretical Schwarzschild black hole. We didn't do anything in class with more than one black hole, and the Schwarzschild metric doesn't. I mean, it just accounts for a single one, and then we look at the singularity points at 2m and r equals 0. Yeah, so this is the entire universe shrunk down to a conformal treatment.
So those Penrose came several years ago, many years ago, I don't remember when, and not only is he a gifted, theorist in physics, but he can draw.
Yes, he can. Yeah.
Like, yeah. Yeah.
He came to UGA?
It was 3 series of talks. I want to give a talk here. When long time.
That would have been amazing to go to. Yeah. So for me, one of the questions I wanted to answer was, okay, are we preserving physical meaning when we do all of these coordinate transformations and diagrams? Like, yes, it's nice that I have this conformal treatment, but does it actually mean anything when I try to put light cones in? And the answer I arrived on was loosely yes, because I can come and draw this conformal treatment and still put in light cones. But we know from in class, an in-spiraling photon into a black hole will appear to freeze on the horizon. So from the point of view of the photon, this is a true boundary. I mean, it's not going past. But we know from our point of view, it will be able to pass the singularity. I think if we recall the movies you made for us, we had the quick in-spiraling that got faster and faster, and we made an infinite number of revolutions and froze on the horizon. So from the point of view of the photon, it can't actually pass this. But if we take the outside frame of reference and allow it to go through, then it should actually go into these regions and reveal all of these other region 3 and region 4. And if you take the Kerr extension and go all the way into tiling this whole board up and down, you should be able to trace those passive photons through. The only thing I'm not sure about, and I would probably like to look into myself, is can you go through the singularity? Because that should come out into a white hole, but and what does it mean to go beyond r equals 0? It's r equals 0. It's a radial coordinate. It doesn't mean you can't go into r. I don't know. So strange things are happening there.
So all of this is based on conformal
Yes.
metric.
Yes.
What if you solve Einstein's equations and end up with a metric that is not an arbitrary metric? Is it still possible to draw a Penrose diagram for that?
Well, I would imagine so, because we were intentional about the conformal treatment here. We lost our metrical meaning when we imposed a conformal treatment of it, and then had to regain that by doing another coordinate transformation back into a space-like and a time-like coordinate. So I don't see why you wouldn't be able to do a similar process for any arbitrary metric and take infinity and bring it down to something we can consider as a boundary. You might lose your metrical meaning in the process, but I would assume you would be able to transform back into some metrical frame where your null geodesics would hold up and give you something meaningful. Any other questions?
No questions, guys? Pretty heavy. All right, well, let's thank Neil for.
Thank you, guys.